Hello, today we are going to talk about recurrent neural networks. It's one of the fundamental blocks of language processing, and I hope by the end of this lecture you can appreciate why that is so. So, first, the point is um, you have to think why such a network was required. When we have a normal multi-layer perceptron, what is the advantage of using a recurrent neural network? Scientists found that the normal multi-layer perceptron does not model sequences. That's because one of the issues is that it has a variable length, which you have to take as input and output. Now, in language, you can see it as a sequence of characters or a sequence of words. So let's see how we can use this flavor of neural networks to help us process better. So the first is how we are representing these neural networks. We have seen this multi-layer perceptron n number of times with the input and the hidden layer and the output layer. Now, just for our convenience, we're going to rotate it. So now our multi-layer perceptron is going to look like this, with this being the input, hidden layer, and output. So bear with me. So this part is going to be represented this way. That is, I have an input x1 and there is a hidden state here or a hidden cell and there's an output. Now it might be that x1 and out1 are just one input and one output, or it could also be your input itself is composed of other inputs. We'll be seeing these variants, but this is the general building block of a recurrent neural network. Instead of going from side to side, we're going from bottom to top. So this is known as a feed-forward cell. I'll add more details later. So now, what we're going to do is, with this hidden cell itself, we are going to have weights that's going to flow into it. So you're going to have at time n-1 a hidden state and at time n+1 a hidden state. It'll become clearer in the next few slides. So if you have two inputs, there's going to be this enjoining hidden state variable. Now, so all of these are so we can model sequences, right? So not only though the fact that the input is a sequence is fixed, the output may or may not be a sequence. So when you have the input also to be a sequence along with the output, it's known as many-to-many. When your input is a sequence and your output is just a single variable, it is many-to-one. One-to-many is a curious case where the input is actually not a sequence, but the output alone is a sequence. This is not used as it is much, but it's often used in conjunction with another set of networks known as sequence, where you go from many to one and one to many. We'll be seeing that in the next lecture, next week. So to give some examples, when you have language modeling and you want to say RNNs are awesome, you have RNN as one input, output for that is R, then R as input, output is awesome, awesome as input, and end of sentence as the output. This is a typical many-to-many example. Then you have a many-to-one example, where you have a sentence and you find the sentiment. We've been talking about sentiment analysis quite a lot in this course. And you basically input a sentence and get the final output sentiment. So that's a single value. So that's many-to-one. Now, I want you to think, what are the properties of a sequence? In the sense, what are the characteristics of a sequence that differentiate it from a set or a collection? So if somebody could give me some answers, it would be great.
The dependency of like one element on the previous element.
Great. So, oh, I stopped sharing. Is it? I was trying to write it. Just a minute. Okay. So, dependency between elements. Yeah, that's one of the like key features of sequences. Any other ideas? Okay, that's good. So the dependency between elements from the previous to the next. So a sequence dictionary definition is like it's a collection of objects, but it has a definite order. So there are two properties of a sequence that's important and noteworthy for computer scientists. One is order, like you said, the previous depends on the next, or next depends on the previous, but the order is important. And the next concerning feature is that the length of the sequences might vary. So if I have a sentence, it can be of size 5 um, words or 4 words. I can have a word like catch, where cat itself is a word. So the sizes of the sequences vary, but the language is the same. How do we model this? Where though the sizes are different, the underlying model is the same. So these are the two properties of sequences that recurrent neural networks try to address. So this is the recurrent part. What does this mean? So we will be seeing an example. It's basically a multi-layer perceptron with the additional temporal constraint of time. By time here, it indicates the order, like we saw the previous and the next, the connection. So that order is referred to as time. And we are going to model how this network accesses that order or time. So we are having this cell and it's concatenated. So you can imagine these themselves are multi-layer perceptrons, and we pass this extra connection. So in a multi-layer perceptron, you will have this individual cell, individual cell, individual cell, but we are adding this extra parameter. So before we had only the hidden input and output, but now we have this connection. And this is why it is called recurrent, we will see momentarily. So the first thing to note is that the weight we have here, it is the same. It is not V1, V2, V3 like how we had in our W matrix. It is not changing. It's a all the weights across time steps are the exact same. So that is a feature. Why are we doing this? This is to ensure that no matter what length of the sequence, we are modeling the language. So this ensures that arbitrary length sequences can be used. So one property of the sequence we have taken care of. Then the next part, the fact that it travels from the previous time step to the next time step, this encodes order information. So ht, the hidden state at time t, is going to depend on the hidden state at time t minus 1. Because here we are going to have a function, just like our activation function, which is going to pass hidden state t minus 1 along with this weight v and create our hidden state t. So The fact that this V is constant often allows us to represent this way. And that is why it's known as a recurrent neural network, because it you might have learned recurrences where you have Fibonacci series or something like that, where um, f of n is dependent on f of n minus 1 and f of n minus 2. So this is the broad level idea of a recurrent neural network. Now we're going to see how we are going to build it, how we are going to use it, how we are going to train it, and what are the advantages and disadvantages. That is the overview of today's lecture. So first, how is our input? So we have this input X, WHH is the weight matrix for the hidden state, and then we have outputs. So if it's X0, O0, XT minus 1, OT minus 1, and so on. With time, it's called unfolding or unrolling or things like that. Now, as I said before, the hidden state T is a function of hidden state T minus 1 as well as the input. So we saw that HT is a function of both V and XT, and V, not only V, HT minus 1 and V. So that way you are not only are you capturing the sequence information from the previous state, but it's also a function of your current input, which is also important in your language modeling tasks. And we'll see that these recurrent neural networks handle many types of sequences, and we can have a discussion on what other applications are there. So mathematically, your hidden state is a function of previous hidden state and the input. Now, we usually use tan h or any other activation function. And it's also a function of the weight. So the WHH, HT minus 1, WXH, HT. So XH is going to be this weight matrix. So the notation is that between the hidden states, we use HH. Between the input and the hidden state, we use XH. The catch is WHH is fixed. That is why we have this notation. So we'll be seeing the advantage and disadvantage of that. Here, the author has taken an example where the output is softmax. As we saw, softmax is to generate a probability distribution, but we can have other outputs as well depending on the task. Now, how to train this recurrent neural network? Do you think backpropagation is enough? Or if not, can you think of any problems why it might not work? Just think along these lines. In backpropagation, we have input, output, and we have a weight matrix that we keep updating. What is the complication here that will not let you update? Okay, I'll proceed. The thing is, whether it was our weight, the original version of gradient descent or the stochastic version, we were updating weights either across the entire data set or one step at a time. Now that is not possible because all the weights are constrained to be exactly the same. So in backpropagation, we will fast feed forward the output and backpropagate the errors. Here it is the same, but we cannot update the weights as easily as backpropagation. So the idea is we have the time factor, right? Because of the time factor, we have an extra added dimension, parameter, and so on. So this makes backpropagation a little bit more confusing for recurrent neural networks. But we can still use it. It's just that you have to do it across time. What does this mean? So first of all, as we know, the sequences can be varying. How do we do this across time? So yes, excuse me. Yeah. So the idea is very similar to backpropagation. In the forward pass, you compute the existing values. Backward pass, you compute the errors. But right now, you have to be careful that the gradient descent is a partial derivative. That is point number one. And point number two is that your weights are constrained to be exactly the same. So we will see mathematically what that involves. So the first thing is, of course, that output at time t depends on output at time 1 and 2. It doesn't depend only on the output at time 3. So this is how it flows. So when you have error, dou E3 by dou H3, we know that in differentiation, um, you have you cannot differentiate something that is dependent on some other variable. What do we use if a function is comprised of other functions while differentiating? It's just straightforward. Maybe I'm not putting it properly. It's basically when you have this error function that is comprised of the H3 and H3 itself is comprised of H2. So you use the chain rule, right? When you have the different functions. So right now we'll be seeing how the expression will evolve. So dou E3 by dou H3 will be dou E3 by dou H3 into dou H3 by dou H2. So this will start getting multiplied. So that is how the gradient here will develop. So this algorithm, we call it as backpropagation through time. There are two things we have to keep in mind, that it is partial derivatives. Last time, we could simply do dE3 by dW something. Directly, your weight, we could directly find the weight values by differentiating the errors with respect to the weights, because the weights were all independent. But here, when you compute dou E3 by dou W3, you will end up calculating dou E3 by dou H3, and that itself is composed of other functions. So this is known as backpropagation through time. So to summarize, it's more complex than backpropagation. It's computed across time steps, and it involves a Jacobian matrix mathematically, but it's basically that you're computing with respect to partial derivatives. It's just a convenient notation where you have a matrix comprised of the partial derivative. So now we come to the major drawback. So this came out somewhere in the 90s, and the reason that it could not go forward was because of this big bottleneck known as vanishing and exploding gradients for recurrence neural networks. So what does this mean? So assume I have an RNN of 5 time steps, and you're differentiating with respect to the weight. What will happen? So E5 will have H5, H5, H4. It is a long multiplication. Now, when I apply this, what happens is, on an actual example, I end up getting values that are very small here. These are vanishing gradients. So what does this mean? So these values become very small, and in effect, only the ones close to H5. So the fifth layer and the fourth layer values might be accounted into the update. So we know that when we differentiate the errors, we are going to be updating the weights. So the long-term dependencies are missed out. That is one drawback if the gradients vanish. Gradients don't always vanish. We will be seeing under what conditions they vanish. But when they do, it implies that the long-term dependencies are gone. There is no point of keeping an RNN of 5 time steps. You might as well have kept it for 2 time steps. So even if, why does this happen? So the fact that the values are cascaded across time means that even if one gradient is tending to 0, it gets exaggerated because H2 by H1 is going to be very similar to H3 by H2 because it's dependent on those values. So when that happens, these Jacobian matrices, when you compute, will show that the values are very, very small because of this multiplication. Let's take the reverse. Sometimes you will see this happen. You have a huge, huge value and it is exploding. And it is the same reason. Even if one of the gradients move towards a higher value, it gets exaggerated. So it's a byproduct of the design because our function is dependent on the previous hidden value. Even if one of the values is going to go towards 0 or going to go towards a high value, it is going to be exaggerated. But in language, we cannot afford this because we need to model really long sequences. Your sentence could be a sequence of even characters, in which case it's going to be very long. And sometimes in a sentence, you might have in the beginning of the of maybe a paragraph that I went to France, and then you tell this huge story, and then in the end you say, hence I learned French. So um, we need the connection between the first part of the paragraph and the last part of the paragraph. So I hope I've motivated enough that we need really long sequences and we cannot afford these exploding and vanishing gradients. So how do we overcome this? Can any of you think of a quick hack, what you could do so that it doesn't explode or it doesn't vanish?
Adjust at regular intervals.
Yeah, that's a good idea. Who was that? Sorry, I didn't see the
Uh, just call me Shiva.
Shiva. Okay, good idea, Shiva. So it's a very similar idea. Actually, even more simpler idea we're going to see. Adjust at regular intervals is the idea. Algorithmically, what we're going to do, the initial idea is gradient clipping, which is just that if at all some partial derivative goes beyond the threshold, you clip it. You don't allow it to. So um, these are some gradients and it goes above a threshold, then you bring it back down. So you scale it by that value. So this was the initial way of addressing this problem of vanishing and exploding gradients. So this is, as you can imagine, it is simple, it's efficient. But once again, this threshold is something you can't train. So you have to input this as per experience, as per data set. So this we call as hyperparameter. Hyperparameter is something we don't train in the network, but it's something you have to set. Much like um, I don't think we've seen hyperparameters till now. Okay, but in your machine learning course, you might have seen hyperparameters and so on, where you have certain values that are not going to be trained. And as data scientists or whenever you work with data, hyperparameters are bad news because it will involve a lot of experimentation to figure out what is the correct threshold to use. So there are some other ways. It depends on the mathematical background behind this, which I'm not going into. Where when you start the values for the weights, it's not zero or random. There is a process behind this Jacobian matrix, which says a proof, which says that when you initialize it to the eigenvalues, you get better convergence. Next one is use activation functions, which are different from tan H and things like that. So I don't know if we saw ReLU, rectified linear unit, it's basically so a linear line y equal to x is just going to be a sort of diagonal through the graph. A rectified linear unit is 0 and then linear. So what it does is that there is some kind of classification, but it's also linear so that you can propagate it across layers. So what this does is that the exploding or vanishing quality doesn't happen, because in tan H, for example, you are squeezing it to plus infinity and minus infinity. There is in this that kind of large and small values is not possible. The third way is to use dropout, where dropout is basically while training, I don't update a few weights. So what that happens is it sort of forces the network to think, um, even if I don't have parts of the network, how do I predict the output? So these are some of the ways. As you can imagine, they're all a bit contrived. The whole idea of deep learning is so that the user will not put much effort and you just give the data and learn. Now, after I give this RNN and I tell you, you have to be very careful with how you start, you have to be very careful how you train, it becomes hard. So in next week, we will be seeing more sophisticated versions of RNNs that overcome these drawbacks. The last part
Excuse me,
of
ma'am.
it, yeah, tell me.
Ma'am, in the third point,
Uh-huh.
uh, does pauses mean we get rid of those weights? Like
No, no,
we
we
don't
don't get
consider.
rid of the weights. Let's say I have some 100 iterations. Then
Okay.
during, and I say, okay, 2% will drop out. Okay, so if I have 100 weights in total, then two of the weights I will not update in the entire iteration. So what that means is, given my input, with the remaining 98 weights itself, I should get the output. So what this forces things to do is to make sure that um, all the weights or all the hidden nodes are capable of restoring the input to the output. Basically, the thing is, it's not possible for a single weight to model the entire error space, right? But we want to also say that don't be so dependent on all the weights. So in the first iteration, you will say W1, W2, you are not updating. In the next iteration, W3, W4, you will not update. And at that time, W1, W2 will be updated. It doesn't mean that you just drop it and leave it. It's not like that. It's just per iteration, it is paused or dropped.
Okay. Yes.
Okay, I hope that answered your question.
Yes, ma'am.
Okay. So this dropout you can use for any method. It's not just for RNNs. In all your deep learning methods, it's actually um, advised to use dropout because it makes for better training. Similarly, ReLU also will be seeing later that it is used often. Yeah, let's move on. We come to almost the last part of the lecture today, which is on the bidirectional RNNs. So right now, given let's see this example. He said teddy bears are on sale. He said Teddy Roosevelt was a great president. Obviously, you and I can make out that these two are very different sentences. But a recurrence neural network only sees information up to the past. So things like, and this part of the both sentences are exactly the same. So bidirectional RNNs take advantage of this, and they basically introduce sequencing in the opposite direction. So the key idea is that the backward direction is also very important. So in our previous examples, when we have the input and the output, this goes forward. We have same connections in the backward direction as well. Of course, this makes it more complicated, and you're going to have your exploding and vanishing gradients again. But the idea of capturing both directions is what is important here. So when you start working on this, how would you go about it? You specify how to encode the input and output, whether it's a one-hot vector, whether you use the embeddings that we saw last class, and so on. So this, though I said in the beginning of the lecture that we will be handling varying lengths of sequence, as a coder, or when you implement, what you'll do is, of course, you cannot have varying inputs. Your network structure cannot change on the fly. So what we do is that the varying length is addressed anyway by the weight that we have fixed. While implementation, what we do is that we take the longest sequence we have, set that as the vector size, and we have these empty, masked, or padded sequences for the remaining. So for smaller ones, we have this zero vector or something like that, and the network will learn that that is of no use basically. So you run the network and you perform backpropagation through time, you test and report the values. So this is the pipeline of your RNN network. So these are the terms you need to keep in track: RNNs, backpropagation through time, vanishing and exploding gradients, why that's happening. And that's basically the import of today's lecture.